Hi, my name's Andrew McLaren, and I'm going to help you with problems where you have things like 3x squared. I was working with a student who has like dyscalculia kind of thing going on, where a visual here really helped them understand the relationship. So they were asking, well, if you're squaring this 3x, can you just square the x? Why do you have to also square the 3? And so we talked about that a number of different ways using some different examples. Um, you can kind of see in the context here that you can combine like 3 times 5 to get 15 and then square that to get 225. You could also work with like the 3 times 5 and square both of them separately. But that's just not like the standard operating procedure that we do with the type of math here. And you get like the same value. Usually we think about just squaring both of the values in this, but that is because we don't know what x is. So you need to square both x and 3, but you don't do that normally when you're working with actual numbers. You would use that PEMDAS or GEMMA procedure of like working within the exponent and then doing the power um, if it's outside of the exponent. So that's a number of different ways of thinking about it, but what I think really helps is this visual. So if you had x, and let's say x is 3, or 6, then the area of that would be 36, or e squared, because those are our edge lengths. Now if you then were to have a rectangle that's 3 times bigger on each edge, then that's like 3x for our edges. And when you have 3x, you end up having 9 sets of e squared because your edge formula here, you've got like the edges being squared. And you can see that I've got 9 of them laid out in front of us here. You can also take the 36 from like 6 times 6. So you can have 6 times 6, which gives you 36. And then you can also have, what is that, 18 by 18, which is 324. 324, if you were to divide that by 36, is 9. So you've got 9 sets of 36 within that 18 squared. And you can kind of see it visually where there's these 9 right here. So if you have your edges that are multiplied by 3, then you have 9 sets of that original value that you're thinking about. This is the same reason that when you have like meters being squared, you can't just work with like the linear relationship of centimeters to meters. You have to square those base ratios of those linear things. So like in 1 meter, there's 100 centimeters. And so in 1 squared meter, you've got 100 centimeters by 100 centimeters. So it's an absolute ton of centimeter squares within 1 meter squared. So you have to kind of multiply the edges by 100 in that context here, which means that you've got 100 squared for the ratio of the meters squared to the centimeters squared. So to like really help you with that type of conversion, I would recommend students convert like the linear sides first if possible, to help you with the conversions of like the squarings for those types of problems. It's a little bit tricky and a little bit weird as to like why that works out, but in this context you can kind of see the same sort of idea, but it would be just really difficult to draw all those tiny little squares, but it's the same sort of concept where there's like a ton of these little ones within that big one.